Today we'll be continuing with our thermodynamics. So last class period we talked about thermal expansion, and we can understand thermal expansion because as you raise the temperature, what is that actually telling you about the molecules? They're moving faster. And so if they're moving faster, the collisions are going to be harder and they're going to naturally spread apart and become less dense. That's why thermal expansion occurs in almost every material. I wanted to actually go over one homework problem myself because they really did a bad job with the expert TA. And that's the one that says that we're going to model how much ocean levels will rise because of thermal expansion of the water.
No, but it just didn't notice me because it seems so straightforward, but apparently it's not.
Well, the way they did it is more straightforward than it really is. So let's start with let's start with reality. Let's look at reality, and then we'll go to the physics attempt to do it. So reality is our Earth is nearly a sphere, but not perfectly a sphere. And so the lower portions have water in them. And so we have 71% of the Earth is covered with water. And the average depth is 3.7 kilometers. So if that water expands, you're going to have water levels rise, clearly. Now, I looked this stuff up in sending a long report to expert TA, and the reply was, that problem is no longer part of our list of problems, which is really weird because I did not assign it until 2 days ago. But I'll follow up and make sure that they looked properly for it. The approximation, well, okay, so I've got myself off track. I looked it up, and climate experts say that somewhere between 40 to 45% of the ocean rise that will result with increased temperature will come from thermal expansion of the water. You have other things are the melting of glaciers that are on land. Melting of the Arctic ice doesn't matter because it's floating. And what does Archimedes tell you about the water displaced by a floating object? The weight of the displaced water is equal to the weight of the object. So I have ice, which is less dense than water, displacing the amount of water that it would displace that mass in water. Well, conveniently, when ice melts, it becomes water. And so it will displace exactly the same amount when it melts as it did when it was frozen. So the North Pole, its melting won't change ocean sea levels at all. But the South Pole, Antarctica, that is a continental mass. It's on top of rock. And so when that melts, it will then flow into the ocean and raise water levels. Anyway, coming back to this. If you raise the water level, if the water expands, then the water level, let me just change colors. The water level is going to be just a little bit higher all the way around. Which means that you're going to have more land covered. Well, the more land you cover, the less height you're going to rise because you have an increase in volume for covering more land. But since it's 71% covered with water, it's probably fairly reasonable to treat the Earth as if, and so here we're going to a physics model that says the Earth is a sphere with water completely covering the surface. If you were to take that with the same numbers here, and you have 100% coverage, it would be about I think it was I can't remember the number. Something like 2.6 kilometers deep, covering the entire Earth. Now, we're not going to work with that 2.6. We're just working with 1 kilometer for our depth. And the wording of the problem suggests to me that this is the model that they're using. Now, if that's the model they're using, then if you want to be really, really honest, the change in area here to here is very small and can be ignored. And so we could treat it kind of like it's just a fixed tub with the area here being a fixed amount and then water. That didn't change color. Then water filling up to a certain height. So there's the L. And so what's the equation for volume here? If I have a fish tank with an area of the base is A and a height of the water is L, what's the volume? Go ahead, you say it out louder, Sarah. Okay, I use L, so I'm saying A times L, but yes, exactly what you said. So the volume is the area times the length. Now, if we heat this up, the area is not changing because the Earth is a rock that's not going to expand very much. So for our purposes, we're saying the Earth isn't expanding, the area is staying the same. And so all of the change in volume is just going to be constant area times change in length. So therefore, change in volume should just be area times change in length. Using our equation for volumetric expansion, change in volume is equal to the original volume times beta delta T. And then using this, that should be equal to area times change in length. The original volume would just be the area times the original length. And now we're down to the equation for the change in length. It should be that. And if you calculate now, it's really simple. They gave us beta, the coefficient of volumetric expansion, is equal to 210 times 10 to the minus 6 per degree Celsius. The original length they gave us was just going with 1 meter, or 1 kilometer, excuse me. They want the answer in meters, so I'm just going to put this in meters. And then the change in temperature, which was 1 degree Celsius. I think we can all do this math in our heads. 1,000 is 10 to the third. 10 to the third times 10 to the minus 6 is 10 to the minus 3. So that's 210 times 10 to the minus 3 meters equals 0.21 meters. That's what I consider the correct answer. How many people got that answer?
I have a question.
Yeah.
Wouldn't you convert beta into alpha?
That's what they did, but it's wrong, is the problem. That's what the website did. The website says, okay, it's an isotropic material. Water's isotropic. That means its expansion is going to be the same in all directions. All fluids are isotropic. Only things that are crystalline or solid can be non-isotropic. So water's isotropic, so it should expand the same in all directions if it is allowed to expand. But remember, water is a fluid. It fills whatever shape it's within. And we had a constrained area. The area of the surface of the rock Earth is not changing. And so the water can't expand to the sides. It can only expand upward. And so they were saying it's not exactly 1/3, but it's approximately 1/3 of the expansion would be in each direction, and we're only looking at the vertical. And so they get 1/3 of this because they just said it's 1/3 vertical, 1/3 horizontal this way, 1/3 horizontal this way. But it can't expand in the horizontal directions. And so that's why their answer is clearly wrong. So I will go through and I will give you credit with either one, either their answer of 0.07 or my answer of 0.21. And since everybody has the same numbers, better all get it. And I'll go through and I'll grade manually for the people who put in what I consider the correct answer. Yeah.
So if we got that answer the first time, we'll get our points back.
Yes,
then?
that's right. Just like we did with the other errors we recently had. Yes.
So, I mean, for us who didn't do it, which one do you want us to put? That one or the...
Put the 0.07 because it'll give you credit and I don't have to hand grade it. is it clear to people what the difference is in the two methods?
One is growth in all areas. The third is just the growth in
Yes. Yeah. Good summary. All right, so that's our homework problem. I know I took a long time. Hot air balloons. Anybody here been brave enough to be in a hot air balloon?
Give me a chance.
I said has been brave enough.
Oh, no.
Yeah. I am not brave enough. I don't ever intend to do that. When we first came to America, my parents took me to Disneyland Knott's Berry Farm, and they have this parachute drop. That's tied to cables, and I was still petrified. But hot air balloons work for a very simple reason. You heat the air up, and what happens to the molecules when you heat them up? When the temperature rises, the molecules do what? Move faster. So because the molecules are moving faster, they bump off each other harder, and they expand. So you have the same number of molecules, but a bigger volume because of the expansion. Question, Ryan?
Yeah, did you say when you came to America?
Yeah. I was born in America, but I was 5 years old when I left. And,
How long were you there?
only 5 years, actually.
Where'd you go?
I lived for two years in Sierra Leone. That's where I did the whole fire walking, melted my feet and stuff. And then 3 years in Liberia. You guys just don't know anything about me, do you? Yeah. Okay. Just the sort of, I was thinking about this morning as I was trying to clip my deformed toenails. Okay. So physics, who cares about physics? Read about Richard's history. Yeah, some context is necessary here. First of all, my dad accepted a call to be the principal of Yili Mission in Sierra Leone. And the problem was mom was pregnant with me. And so he got permission to stay until I was born. And then they said, look, you can't wait any longer because I was 2 weeks late. You have to come now. We can't start schooling without you. So my dad left for Sierra Leone. He and my mom had agreed that I'd be named Thomas Lee Webb. It was 52 years ago, about today, when my dad left the country. And so my mom finally gave birth to me 2 weeks late. And I've always known that I was named after the physician who delivered me, but I did not know that it wasn't until I arrived in Africa at the age of 5 weeks my dad found out my name wasn't Thomas. So we get there to Yili Mission. They had already started the school year. They just made my dad the vice principal, so he was like extra angry. They made him leave. And they had wood-burning stoves in their cafeteria they did back then. And so one Sunday, I was 13 months at the time. My dad was walking over to the shop to do some machine work, and he noticed these coals out in the road. He's walking through his booth saying, I wonder if they're hot. We got into the shop, and he was just lighting up his acetylene torch. When he thought he heard something, he looked out, and he saw me standing in the middle of the coals. So my dad went running out there. Meanwhile, my feet were burning. Not fire burning, just burning.
Yeah.
And so because it was hurting, I started crawling. And so I have like visible scars on my wrist, not a suicide attempt. It's from melting them, crawling in the coals. And so that was hurting too, and so I sat down.
Oh, no.
I was wearing a diaper, and the diaper saved my butt. Yes, my favorite part of the whole story happened at that one. So they took me to the leprosarium. I was treated with single leprosarium by a physician who was a Union College graduate. For the first 2 weeks, they just assumed they were going to have to amputate my feet, so they didn't even use sterile dressings. But I didn't get any infection, so they're like, well, I guess he'll keep his feet. We better treat them like we would a normal patient. And they tried to keep my toes apart, but the scar tissue just made them merge into one big flipper. And so when I was 2 years old, we came to America to have surgery to separate my toes. They did skin grafts, so I've got an ugly scar on my belly from where they took the skin to put on my toes. And thus in high school, I was teased as being a hobbit because of the prolific hair growing between my toes, because in puberty, I developed a hairy chest, and it also has the hair follicles down there on the transplanted skin. And so came back, Liberia for 3 years, and then came to America where I grew up. There's the story.
Cool.
Yeah. Not much physics involved with that except for firewalking. When we talk about firewalking, remember, firewalking is not always safe. Theoretically, if you have, your feet are a little bit damp and you don't have prolonged contact and you have ash, you have wood that has already been burned, it's a pretty good insulator, you can do firewalking without a problem. But I still don't recommend doing it because things can go wrong, as I attest to. Back to this. Hot air expands because of the higher kinetic energy. But because it's expanded, you have a bigger volume for the same number of molecules, so it's less dense. But we learned from Archimedes, once again, that less dense things float on more dense things. And so a hot air balloon, you have the total weight of the balloon with the hot air inside plus the basket underneath with the people and whatever is less than the weight of the air that's displaced. Once again, Archimedes' principle, the buoyant force is equal to the weight of the displaced fluid. In this case, it's air that's being displaced rather than water. And so that's what makes a hot air balloon fly. And, it always seems just a little tenuous that you are blowing some basically air into this balloon and it somehow stays up. But it's because that air is less dense because it's hot. And why did that go to a new slide? I don't know. What I do know is I'm not supposed to press that button in this program. It just made a new slide for me. Thank you. Or a new presentation, actually. So let's talk about ideal gases, because we're going to talk about ideal gas law primarily today. So ideal gases. How many people have studied ideal gases? Okay, not as many people as I thought. I thought general chemistry studied it.
Oh, okay, that's what you mean. I meant actually.
Yeah.
Observe.
Okay, so one thing a lot of people miss with ideal gases is ideal gases are not real gases. They're ideal. They're idealized. Now, a lot of gases are very close to idealized. So the first thing I want to emphasize is what property makes a gas an ideal gas? What's an ideal behavior? So I have two of them listed up here. Without looking there, I'm going to guess which one's number one. Number one is that they simply don't interact unless they touch. Is that one or two? Good. They don't interact unless they touch. So think of it like this. I come over and I come close to Nathan. If I don't touch him, I don't deviate at all. If I touch him, then I deviate. Meanwhile, the lawsuit. That's how my son's going to become wealthy. Anyway, so that's an ideal behavior. Now, if we think about it, there's a first thing that's absolutely necessary. Gravitational force between Nathan and I was so small we didn't worry about it. But if I had an electric charge and he had an electric charge, it probably would have made a difference. So an ideal gas is going to have to be uncharged. A plasma, a charged gas, is not going to be ideal because it has interactions. And the second thing is what happens if they collide. If you have a perfect collision, what happens? If they're not interacting, they're going to collide like billiard balls. Bounce off elastically, no loss in kinetic energy, just change in direction. So those are the two things that go into the atoms being non-interacting. They need to not interact unless they touch, and if they touch, they need to bounce off elastically. The second one, zero volume. Now we know atoms are small, but they still have a finite size. The second ideal property is zero volume. So when we talk about ideal gas, we're making the approximation that the molecules have no stickiness. They don't have any attraction to each other when they touch. And we're making the approximation that they have no size. How do we make this occur in real life? Well, you know that we treat a lot of gases as ideal, right? You obviously learned the ideal gas law. Did you learn the van der Waals equation at stage? Van der Waals has two parameters, one for the stickiness coefficient and one for the volume coefficient to make it more realistic. I was talking to Dr. Osborne, he says, Yeah, we have another one we use. Don't tell me about the other one. In my physics classes, we treat the van der Waals as it takes care of our problems. Because, trust me, when you're taking the advanced thermodynamics class, it becomes more difficult. So how do we approximate these? Okay, yeah, I don't have a slide on that. We approximate them first for the zero volume. Okay, so I went to the second one. For the zero volume, if the molecules are very far apart compared to the size of a molecule, then you could treat the molecule as having no size because the separation is very big compared to the size. If you do a ratio, it's close to zero. So a low density gas is a gas that's going to have big space between molecules. Hence, we get that second state if we have a low density gas. The first one with the elastic collisions, let's suppose that you go back to the lab we did with the carts colliding, and you had the Velcro to hold them together. If they collide slowly, they hold together nice. If you collide harder, what happened? They bounced off each other. If you collide harder, the stickiness becomes less important. Basically, if the total kinetic energy is way, way bigger than the energy that you can have holding them together, that energy holding them together becomes insignificant. And so it's going to behave ideally if they're traveling really fast. What parameter, which of our macroscopic things tell us about how fast they're traveling? I've said it 4 or 5 times already today. Not heat, but you're in the ballpark. Okay, the temperature, which is proportional to the average kinetic energy. So high temperature and low density are the two things that approximate ideal gases. Of course, high is a relative term, low is a relative term. So for high temperature, we say not close to the temperature of, for some reason, the technical word just escaped my mind, liquefaction, that's the technical word. Not close to the temperature of liquefaction, which means not close to the temperature of boiling or condensation. So for water boils at 100 degrees Celsius. If you're well above 100 degrees Celsius, water will behave as an ideal gas. If you're like 110 degrees Celsius, it's not close to ideal gas because there's a significant stickiness compared to their temperature. And then low density, well, low density is really quite a variable term. Now we have some gas laws, and I didn't go with my most prolific slide here. The work was done, actually a lot of this work was done by the same guy, but we have different names for the different laws. So Charles' law, named after a dude who's, he's French, I'm sure they don't pronounce it Charles, but that's his last name, Charles, in English. He studied what happens if you keep the number of molecules in a gas constant and you keep the pressure of the gas constant. In fact, everything we're going to look at here is keeping the number of molecules constant. I'm not going to say that anymore. I'm just going to say keeping the pressure constant. So Charles said if I keep the pressure constant and I vary the temperature, what's going to happen to the volume? So an example of that would be like a balloon. A balloon, believe it or not, the rubber's not doing a real big deal on it. It's mostly atmospheric pressure outside, so we treat it as roughly constant pressure. Or if you want to be really correct, you just take a cellophane bag. You blow up the cellophane bag about halfway, and then you heat it up, but keep the outside's atmospheric pressure. What's going to happen? The volume increase. The volume increase is proportional to the temperature. What units do you need for temperature to do this? You need kelvins. You can't use Celsius degrees. There's a number of different arguments for it, but let's just make it clear. You have to use an absolute temperature scale, a temperature scale where 0 corresponds to the minimum possible kinetic energy. So if you're using Charles' law, make sure you use Kelvin temperatures. In fact, at this point in time, almost always you'll get the right answer if you use Kelvin. Some of the time you'll also get the right answer if you use Celsius. And there will be rare instances where it should have unit indications where you need to use Celsius. So if in doubt, use Kelvins. So you have for any gas, any volume, if you double the temperature, that is you go from, let's say, 300 kelvins, room temperature, to 600 kelvins, the volume will also double. You guys remember Deflategate in football? That's what's going on here according to the people who apologize for the cheating. They say, well, we know that the temperature dropped, and so the pressure dropped because the temperature dropped. Well, keep in mind, the temperature, it wasn't even cold. It was like 45. I mean, we got lots of people here from Colorado. 45 is not that cold, right? So you go from measuring the pre-game ball temperature like 72 and you drop to 45, both in Fahrenheit. Convert those to Kelvin, it's not a very big drop. And so the pressure could not have dropped the amount they say. Now I have to also say, you'll find physicists who disagree with me. Dr. Timothy Gay at University of Nebraska wrote a thing about it. But you also have to know that Dr. Timothy Gay at University of Nebraska was a high school football teammate of Belichick's. They're good buddies. And so he was right to defend his buddy. So what?
Just another cheater.
Not going to disagree.
So if I gotta go to court, you have my back, right?
I got your back, TJ. Yeah. He's got a speed ticket. He's going to call me in. We did the physics. He couldn't have been going that fast. He was going half a mile an hour slower than they said. Got your... Okay, so that's Charles' law, that the volume increases as temperature increases. It's a linear relationship, but you have to be using absolute temperature. Oh, I pressed the button again. Right, when I use PowerPoint, that's the right thing to do. When I'm teaching or when I'm using OneNote, it's the wrong thing to do. So one other thing to note, no matter what volume you start with, what temperature you start with, what gas you start with, if it's ideal, the line will extrapolate back so they all meet at zero volume at the same temperature. That's actually our first indication of an absolute zero temperature, because at that temperature, the lines would extrapolate to zero volume for everything. Notice I did say extrapolate. What's going to happen if I take my ideal gas and cool it enough? It can become a liquid, which is no longer a gas and no longer can obey gas laws. Can you have a question, Mike? Here? Wow. Can't believe I said the wrong name after county semester.
I have a question.
Yes, Leslie.
So, I'm going to be honest, I didn't really understand what you said about the extrapolating thing, that it'll go to zero or whatever.
Okay, that's what this picture here is showing. No matter what gas you use and what your starting conditions are, you take data from here to here, and then you extrapolate that as you just extend the line. When I was in graduate school, we like to use the term, we boldly extrapolate, because we're being a little brave and trying to extend it where we know it doesn't correctly go. Then they all meet at the same point here.
Okay.
All right, next we go to Gay-Lussac law. Gay-Lussac was the dude's last name, just to be clear. Both Charles and Gay-Lussac worked on this one. It wasn't just Gay-Lussac alone. And this here was studied for a dilute gas where the number density is low. Well, number density is low. That means that was one of our two properties for an ideal gas, right? So this was studying for ideal gas. And here he kept the volume constant. I actually have a little bulb, probably bring it out. Not today. Don't have stuff set up with boiling water. I have a little bulb that we can easily do a reenactment of Gay-Lussac's experiment. And what he found was if you keep the volume constant and you heat up the gas, that the pressure increases proportional to temperature. Again, what units must you use for temperature? Kelvins. So we have the volume increases with temperature if the pressure is constant. The pressure increases with temperature if the volume is constant. And then we have Boyle's law. Boyle kept the temperature constant, and check what happens if you change. Notice I have a mistake here. The volume is never going to be proportional to 1 over volume. The volume is proportional to 1 over pressure. So if you keep the temperature constant and you change the volume, you decrease the volume, the pressure increases, and vice versa. And finally, among the laws, Avogadro's law that nobody ever talks about says if you keep the pressure and temperature constant and you add the molecules, the volume will increase proportional to the number of molecules you add. Double the number of molecules, you'll double the volume of the gas. And then you just put these all together, and they were all proportionalities. But if we combine all these proportionalities, we get pressure times volume is proportional to N times temperature. And so we just insert a constant here and say pressure times volume equals a constant K ideal gas constant, which starts with the C, times the number of molecules times the temperature. So PV equals, we actually usually say NKT instead of KNT. We like to put the K and T together for reasons that we'll see later. So that's the ideal gas law. Now, almost everybody has learned the ideal gas law, and you probably would have said something different. What would you have said differently? You would have said PV equals an RT. Well, something really important to note here is that this is a capital N. Capital N means the number of molecules. I call it the ideal gas constant. It's the Boltzmann constant here. We call the ideal gas constant is this one here. There we go. Fix that. So a mole is simply a number of molecules. So that number is 6.022 times 10 to the 23rd molecules per mole, Avogadro's number. And so lowercase n is capital N divided by Avogadro's number of moles. And we'll talk about later what a mole is. It's not the definition, where it comes from. And so with this definition, we can just replace n, the number of molecules, with lowercase n, the number of moles times Avogadro's number. And then our ideal gas law becomes PV equals lowercase n times Avogadro's number times KT. And then we just change our parenthesis and say, okay, I don't like that color anymore. That stuff there and define as R. So PV equals capital N KT is exactly the same equation as PV equals lowercase n RT. It's just R is a molar constant, whereas K is a molecular constant. Yeah.
So when you're writing down the law, whenever you choose to use the R, you should use the lowercase n.
Yes.
And then when you switch it, it'll be K and with the
capital N.
Yeah.
That's right. So that's the ideal gas law. And so that gives us lots of simple problems. You can say, I have a gas and we have our variables of state. These variables, pressure, volume, number of molecules, and temperature, are variables of state. Those are variables that tell us what state we're in. Doesn't matter how you got there, they tell you what state you're in. We have other variables that will matter on how you got there, but those don't. So oftentimes we keep the number of molecules constant. In physics, almost every time. See, we physicists are different than chemists. Chemists do experiments and they do things like mix chemicals. And so you usually have to take the stopper off to do that. In physics world, we don't want to take the lid off. We leave the lid on. And so the number of molecules stays fixed and it makes our calculations a lot easier. So, let's be honest, the chemists don't have generally the option of keeping the number of molecules fixed because you're going to have evaporation and whatnot. And so they have to do things a little bit differently in their calculations because of that. So you have different types of systems, as we call them, in thermodynamics. You have an isolated system, a system that has no interaction with the rest of the world. No heat can flow in or out, no work can be done, it's isolated. You have a closed system. It can't exchange molecules with the rest of the world. And then you have an open system, it can exchange everything with the world. Chemists work in the open system world, physicists generally work in the closed system. Isolated system is too basic. I said I was going to do a long derivation. I probably won't. We only have 14 minutes left. We'll get it started at least. We now can do things like the football problem. Instead of doing this, let's do the football problem. So we have a football. Let's say that the official has a very hot room where he is testing the temperature or the pressure of the ball. So let's say that we have the temperature 1 is 78 degrees Fahrenheit. We'll need to convert that to kelvins. How do we convert it to kelvins? Okay, we know that temperature Celsius is equal to temperature Fahrenheit minus 32 times 5/9. And then to get kelvins, we'll have to do that plus 273.15. So what is that initial temperature in kelvins? What is it?
298.5. Does it go on forever?
Yeah, I'll go 298.5. Okay, then we had, during the football game, temperatures got as low as 45 degrees Fahrenheit. So we need to convert that to kelvins. So it's 45 degrees Fahrenheit in kelvins.
$280.2.
All right, so now we just go to our ideal gas law. Assuming that it's a non-leaking ball, we have NR is equal to PV over T equals P1 V1 over T1 equals P2 V2 over T2. So the volume of the football is fundamentally not going to change. It's going to stay almost exactly the same regardless of the air you put in because it's built to be a certain size unless you completely deflate it. So the volumes are the same. So I get pressure 1 over temperature 1 equals pressure 2 over temperature 2. That's going back to one of our earlier, was that Gay-Lussac's? Yeah, going back to Gay-Lussac's law. So that means pressure 2 is equal to pressure 1 times temperature 2 over temperature 1. Equals, okay, now we have to look up numbers. What is the pressure you're supposed to inflate the football to? Anybody know? I believe it's 13.2 pounds per square inch. So if you put that in, what do we get for the pressure we would have in that ball at that really cold 45 degrees? How much? Okay, so he has 12.4 psi. I believe all but one of the balls were below 12 psi. 12.5 is the minimum allowable pressure. It doesn't seem within the laws of physics for this to have occurred naturally. Good thing I recorded this. So some Boston Gomer's going to call me up. Okay, kinetic theory of gases. This is a derivation that I know students find tedious and annoying. But I think it's important to help us establish what's really going on when we talk about the kinetic theory of gases. So the kinetic theory of gases is doing statistical calculations to relate temperature with the speed. I have said from the get-go that temperature is a measurement proportional to the average kinetic energy. This is what establishes it. So we start by saying that I have a box, and the box, do I have a better picture here? Have a better picture. Yeah. The box is filled with molecules, and first I'm going to look at just one molecule and calculate what's going on with the one molecule. And then we're going to expand it to looking at a bunch of molecules. So if I have one molecule, when that molecule hits the wall, it's going to put a force on the wall, right? That's pretty obvious. And we've learned from Newton's second law that I can relate the change in momentum to the force. So I have a box of length L in the x direction. And I have a random molecule with speeds in the x, y, and z directions. When it hits the wall that is normal to the x direction, the only change in velocity is going to be in the x direction. The y and z components are going to stay the same. So when it hits the wall, the change in momentum vector will just be the momentum final in the x direction. Well, minus the momentum initial in the x direction, all in the x direction. I'm going to drop the vector sign immediately, but I just put it here to make sure we have, that's the full change in momentum. According to Newton's second law, how do I relate change in momentum to force? Everybody should be able to quote Newton's second law. Net force equals, is what? Okay, mass times acceleration. That's the form that's correct if the mass is constant, which is the case here. But the general form, the one that's always true, is change in momentum over change in time. So I dropped the vector signs here. The net force is change in momentum over change in time. So my change in momentum here, if it's an elastic collision, I'm just going to go from going this direction to this direction with the same speed. So my change in momentum, who cares about the minus sign? But it's 2 times the initial momentum in the x direction. Or and I drop the initial now, minus 2 mass times v in the x direction. The minus sign just has to do with direction, so up here I'm just going to put for delta p, 2 mass, speed in the x direction. But I need the change in time. There is nothing in this world that's going to tell me how long the particle was touching the wall. So I cannot determine the average force during the collision. But what I can do is calculate the average force for a longer period of time. That particle is going to bounce around, come back and forth, and the x component of its velocity is completely going to describe how long it takes to come back and hit the wall again. So I can calculate the time it's going to take to go from the wall to the other side and back and find the average force for all time for this one particle. So if I have a particle that goes a distance L and back, what's the total distance covered?
2L.
2L. And it has a speed of Vx, How do I go from the distance and speed to the time? With the ratio. We know that speed is distance over time, so time is distance over speed. So if I put that in here, I have the net force average is mass times the speed in the x direction squared divided by the length. Now we have a little, well, first let's go to pressure and then let's do the magic. How does force relate to pressure?
It's the area, or when it's divided by area.
Pressure is force over area. So that means that the pressure that this is going to put on, this one molecule is going to put on, my brain was jumping ahead. For a box with an end of area A and a length of L, what is A times L? Volume. Now this, of course, is not a general proof. It's a specific case proof. Now this is starting to look more familiar. If I multiply both sides by V, I have PV is equal to mVx squared. Now is where the little magic steps occur. I was talking about one molecule. What if I had two molecules? What would that do to the pressure?
Increase it.
It would increase it. I'd have the same amount from the second molecule. And so I'm just going to multiply it by n, but there's another step I have to do before I get that. Because if I start multiplying by n, the molecules could have different speeds. And so I need to work with, okay, how is this whole speed thing going to work out? So I have, notice it's Vx squared. So we're going to do two things with Vx. First, our total I should have put vector signs over those. I should have put hats. Our total velocity is the component in the x direction, in that direction, plus the component in the y direction, plus the component in the z direction. The direction we artificially chose, that is, there's nothing to specify what the x direction is. So I should have the average speed in the x direction is equal to, and actually, this here is silly. Those greater than or less than signs mean average. Why is this silly? Because the average speed in each direction is going to be 0. It's got as much positive as it is negative for the average velocity. Instead, what we do is we have v squared is equal to vx squared plus vy squared plus vz squared, finding the magnitude. And the vx squared, vy squared, and vz squared, the average of Vx squared should equal the average of Vy squared should equal the average of Vz squared. And that means that if I take the V average, or the V squared average, that's plus so that's 3 times the average speed in the x direction squared, or the average of the speed in the x direction squared. So I'm going to put this in and say that for n particles, pressure times volume is equal to, since that's Vx squared, So that's going to be now I have something that even looks more familiar. N times that. So if we compare this to the ideal gas law equals NKT, then we must have temperature average is equal to, well, K times temperature average is equal to M times V squared average over 3. So that tells us, well, kinetic energy average will be average of 1/2 mv squared. Since m is constant, that's 1/2 mv squared average. So I can substitute the mv squared average is equal to 2 average of kinetic energy, and substitute that up here. So there we have a relationship between temperature and the average kinetic energy. So we can see that there's actually a legitimate, not so hard to understand, kind of hard to work out, relationship between the temperature and the kinetic energy average. Okay, I've run 2 minutes over. Have an excellent weekend.